Good, welcome back. We're going to calculate some serious calculations today. And I asked you at the end of last class to bring your calculator, get that baby out. We're going to use it out the wazoo. We'll do some multiple choice questions in a few minutes too, but definitely some calculation. Last time we talked about the Stardust mission, the Stardust spacecraft, its tennis racket collector aimed at capturing stuff from the coma of Comet Wild 2. And here's a picture of the various orbits. You can see up here, so here's Halley's Comet, which, if you see it, it dips almost out to the orbit of Pluto before coming back. Here's one that came about 20 years ago, Hyakutake. And I remember taking photographs of Hyakutake, with my regular old camera. It's pretty cool. That's a long period orbit, so its aphelion is way far away. Here's Wild 2, and you can see that Wild 2, this blue orbit, barely dips out to the level of Jupiter. So it's always fairly close to, Jupiter's, for a human is a long way away. But for spacecraft, Jupiter is doable, without too much difficulty. According to what we have now. And here's Temple 1. This is the one that we banged the dishwasher into. And it dips out about to the orbit of Jupiter. And these two are very circular. Halley is, of course, very elliptical, and so is Hyakutake. But, orbits, the comets and stuff, they have all different kinds of orbits and stuff, or all kinds of different shapes. Anyways, here's the tennis racket collector, and we talked about the big hot, I shouldn't say big, the very hot but very tiny hot spot in the Stardust collector. And we're going to get back to that because the important instance of that was the oxygen isotope ratios relative to SMOW, standard mean ocean water, for our planet. So let's get back to that. And we're going to start calculating here in a minute. And you're going to want to make notes on the formula. The formula looks the same for every isotope ratio that we calculate relative to SMOW. But the actual computation, you'll be putting slightly different numbers and stuff. So take notes carefully. All right, now we know what the relative abundance of 17 and 18 oxygen are for SMOW. The mean ocean water of Earth is about 2005.20 parts per million. Oxygen 18, that's the heaviest of the stable oxygen isotopes. And then 17 is also a heavy isotope relative to oxygen 16, the most abundant. And oxygen 17 is at about 379.9 parts per million. Now, if you were a Martian astronomer or a Martian scientist, you might do standard mean ice, standard SMMI, standard mean Martian ice, because that's what they have a lot of water ice subsurface of Mars and up at the polar ice caps or something. But here we do standard mean ocean water because it's the most accessible to us. And if you were up on Mars and you did SMMI, you might come in slightly different ratios. You might come in 2004.3 for oxygen 18 and 384.7 for oxygen 17. It's going to be close, but it might not be exactly the same. Matter of fact, I bet somebody actually knows the answer to that. Somebody at NASA. Anyways, what we're going to do is use a meteorite. So we're going to use this example here. And go ahead and just jot, this is meteorite X. some imaginary meteorite. And we're going to say that it's oxygen 18 abundance, 2406 parts per million, just to say that we've got a fairly nice round number. And notice it's a little bit higher than SMOW, so it's enriched relative to oxygen 18. Now, oxygen 17, 3B, let's say that we got a meteorite and we've analyzed it in our analyzer and it comes back 342 parts per million. All right. Now let me ask you this. Is this enriched or depleted in oxygen 17 relative to SMOW? It's depleted. So make a note of that. 342 is less than 379.9. So it's got oxygen 17, but it's a little bit less than, standard mean ocean water. And, you can have, meteorites, comets, asteroids and stuff, and you just got to check because they can be different, because they can be wildly different. All right, so now the objective or the thing that you check, if you're a scientist analyzing this meteorite, what you check is something called the delta 18 oxygen ratio and the delta 17, and that's that kind of little curvaceous D, that's Greek letter delta, lowercase, and it symbolizes Greek letter delta, D for delta, D for difference. What we're doing is a numeric comparison with standard mean ocean water of Earth. Now, if we were doing carbon, if we were doing delta 13 carbon, we would do something other than SMOW. But for hydrogen, for oxygen, yep, we use standard mean ocean water of Earth. Okay, so basically what you do is you analyze in the lab and you get your number up here, all right, for your meteorite. Okay, so for us, it's 2406. So that goes in the numerator. All right, and then if and that's for oxygen 18. Okay, so then SMOW oxygen 18 goes in the denominator. All right, so you compute that and you're going to get IQ test. Mental arithmetic IQ test. That quotient, 2406 divided by 2005.20, larger than 1 or less than 1? Larger than 1 or less than 1? It's larger than 1 because the numerator is larger than the denominator. So you're going to get 1 point something, and then you subtract 1, and that's your delta 18 oxygen for this meteorite. Now, when you do that, do you have your calculator? Who's got that first quotient? It's 1 point. What do you got? In the back. Did you get it? Get your calculator. Who's got it? Okay, over here. Well, anybody else? 1.19988? Good. All right, so that's what I got. There it is. All right. Now, you're going to want to be able to do this on exam 3 and, Daniel, on the final, just in case. I'm not saying it's going to be on the final, but you might want to make sure you know how to do this for exam 3 and the final. So that's fairly easy to calculate. So you just subtract the 1. All right, so there's your delta 18 oxygen. And it's a ratio. And we, it's pretty close to 20 to two significant figures. It's 20%. Now, I'm going to give you another way of expressing that number, but before I do that, I want to pause for questions, because you're going to be doing this on homework over the weekend. Yes, there's going to be some homework. And yes, there is. So somebody's up here in the second row going, no, Dr. Reed, no. Yeah, I'm going to give you some calculation practice, maybe a few concept questions. All right, it'll be ready tomorrow sometime. Anyways, questions on how to calculate this, exactly step by step. Yes? Yeah, I'll give you, the question was on a test and on homework, will we have SMOW? And the answer to that is yes. I'll give you a table. If I ask you to do something like that, I don't, and the reason that I say that, I go by my standard. I don't want to have one standard for me and then expect another standard of you. And I always look it up. So I give it to you guys, so you know, little table on the cover page, and you know, then you got to know what you're doing after that. So, another question. Yes.
So, this final answer, 20%. Like, how would you say that in relation to the entire calculation? Is it 20% more than the abundance? And then, like,
Yeah, what you would say is, you would say that, you know, you don't say, well, it's 20% SMOW, because that's not what you've got. You've got a ratio, 20%, and basically you just quote, my delta 18 oxygen is 0.20 or 20%, or here's the way that's customarily used, per mil. All right, so see that weird looking percentage sign? It's got a 0 on top of the fraction bar, but down below it's got 2 zeros. That means parts per thousand, per mil. Okay, so you would say 200 parts per mil. And you know, the way that I see it, the data for oxygen isotope ratios, you see it in tables, and then you see them graph it up. And one of the ways that we graph it up is we do delta 17 oxygen and then plot it on graph paper, you know, with delta 18 vertical and delta 17 horizontal, and then, you know, do a bunch of meteorites, you know, do a bunch of moon rocks and see what the patterns are. And there are patterns, okay? And we're going to get to that in just a few minutes. One more question. Okay, let's do another meteorite. This is Kalahari 008, and it's a lunar meteorite. Here's another picture of a slice of it. Fairly small slice off the front end. How do we know it's a lunar meteorite? Well, it was picked up in the Kalahari Desert. You know, somebody found it and said, oh, that's a meteorite. And so then they analyzed it, and they came up with delta 17 and delta 18. So here are the specs for Kalahari 008. Now, the lab will give you the abundance. And for 18 oxygen here, it's 2018.27 parts per million. Now, here's related to, with the orange jacket. Second row. What's your first name again? Vince. With respect to your question, when you're doing the delta 18 or the delta anything, you want to make sure that the numerator is, if your denominator is parts per million, make sure your numerator is also parts per million. You know, if your denominator is parts per billion for some other isotope, then make sure that the number you stick in on top is parts per billion. Okay. So let's do this together. Let's do delta 18, and you're going to calculate delta 17 in a minute here. So let's do another one, and this is a real live meteorite, Kalahari 008. All right, there's my set. I plugged in 2018.27 parts per million. And that's from the lab. That's the guys with the white lab coats and you know, the glasses, and they think they know everything, etc. So the lab guys give you that, and then a bunch of lab guys over the years give you the agreed on value for SMOW 2005.20. That's in the denominator. Okay, and then you go -1. All right. Now, then you calculate that fraction. All right, who's got a calculation? Because you're going to need to do that. Make sure you have a calculator ready. Who's got it? Is it going to be greater than 1 or less than 1? Greater than 1. Numerator is greater than 2005. What do we got? What kind of a number? And I know somebody over here has already gotten it. Somebody over here, what do you got? Raise your hand if you've got it. Oh, there's a lot of slackers in here. Who's got it? Come on. What do you got? 1.00652. Oh, you mean like this? Okay, that's pretty good. 1.00658. Rounds up to 52. Good. All right, so there's your number. And you're going to be doing this calculation in a minute, so you better get your cell phone calculator out or your regular calculator out. Now, this one's cinchy. You just subtract the 1. Look at the oxygen 17 ratio, the abundance for oxygen 17. It's 381. Is that above or below SMOW? It's above. So when we do delta 17 oxygen, all right, now what's your name again? Casey. That's what I thought. Casey, when we do oxygen 17, you're going to get 1 point something again. All right, it might be a different number, but it's going to be 1. So then you subtract, and here's the leftovers, 0.006518. All right, so that's got 2 zeros and then a 6 after the decimal point. So that's basically 6 parts per 1,000 or 6 parts per mil. All right. Percentage-wise, it's 0.65%. Okay. All right, if you savvy me on that. And normally we report in per mil. And your calculation coming up, I think it's the next slide, is going to be, I'm going to ask you to go per mil. So make sure you have this sequence copied down in your notes. Because you're going to get, your calculator's going to give you this, 0 point something, 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 something. And then you can mentally convert that to a percent, and then mentally, or pencil and paper, convert it over to per mil. Basically, it's moving the decimal point. Couple, 3 places, depending if you're going percent or per mil. And sometimes, some isotopes are so rare that you have to go into parts per million again. But for oxygen and carbon and stuff, it's per mil. Question?
How many decimal points are we typically supposed to use?
I'll tell you all the time. And on the upcoming question that you're going to calculate, I'm going to ask you to go to the nearest 2 decimal points per mil. So this one, I would go, if I were asking a question and I want you to type it in, you would type in 6.52. But don't try to type in the per mil sign, but just, the numeric part, okay? But as always, what is your name again? Hannah. Oh, Hannah, okay. Now, Hannah, what I normally do on exams and on clicker and in homework is specify how many decimal points to type in. And I always say just type in the numeric part. So for this one, it'd be 6.52. All right. And conclusion, enriched in oxygen 18. Kind of like the McKeegan hotspot. Although McKeegan was this is warm. The McKeegan hotspot was blazing. It was really hot. I think it was oxygen 18. All right. Now, let me pause for more questions. We're going to go nice and easy. I want you guys to be experts on this. Go ahead.
What if the number that was analyzed is smaller? Would it be negative percent?
Question. What if your analysis returns something less than 2005, for instance? Will your answer be negative? And the answer to that is yes. If you had like 2000 in the numerator and 2005.20 in the denominator, then that's going to be 0.99 something, right? And 0.99 something minus 1 is going to be negatory. And so make a note to yourself mentally that sometimes the delta 18 and the delta 17 oxygen come in negative. And what that means is that you're depleted relative to SMOW, all right, for that particular isotope. Now this one is slightly enriched. It's only 6 parts per mil, but that's considered enriched. And the moon rocks and stuff, and this is a moon rock. It's slightly enriched with respect to the water. You know why? Because it's a rock. You know, there are rocks on Earth that are enriched relative to SMOW because they're rocks. The rocks don't form the same way that the ocean waters do. All right, so it's not surprising that that rocks are different. All right, and this one's different, but not too different. Now, here's famous ALH 84001. And this one is enriched in oxygen 18. And this is the famous one where we think that it is, that this rock contains fossil life form, fossils of life forms from Mars. And some people disagree, and some people think it's got it. I think it's not settled yet, if I recall correctly. Okay, and we have a lot of other meteorites that are measured as well. And you're going to do a calculation here in a second, but let's take a look at some of the patterns. Now, what was your name again? Jacob? Vince, close. Okay. Here's a graph of vertical scales delta 17, horizontal is delta 18. So this is how you see it, the two ratios plotted up. And you can see that, you know, Mars meteorites, they're hunks of rock, so they're not like all at one value, but they do form a line. Okay? And then Earth and Moon are on this solid line. And then this one here, this group of blue squares, they kind of form a line slightly below the Earth-Moon line, and Mars is slightly above the Earth-Moon line. Okay? And those meteorites, the blue squares, they're chunks of the asteroid known as Vesta. So we've got that one. You know, we've been studying Vesta for the past few years. We've got a spacecraft up there looking at Vesta and Ceres. Those are the two of the biggest asteroids in the asteroid belt. So these ones, yeah, they're meteorites. They've fallen to Earth. They're little fragments. And we've analyzed them, and we found, yeah, these things are actually hunks of this particular asteroid. Here's another one. Here's another graph. By the way, go ahead and jot down that if you feel like dipping into and learning more about this. Out in Hawaii, they do a lot of this analysis. psrd.hawaii.edu is a good planetary science research discoveries. It's a really nice website. I actually use it a lot. All right, now this one of the things you might notice about this, there's nothing negatory here. This particular graph, it goes down to 0 on the delta 17 vertical axis, but it only goes to 2.5 on the horizontal delta 18 axis. All right. Now, that's not to say that there's no meteorites or anything else that are negatory, but for this group of things that they plotted, you know, they don't even need horizontally 0 to 2.5. You know, so they're trying to keep it. I mean, you could have graphed it 0 and 0 at the lower left corner if you wanted to, but to save paper, I guess, to make it more compact, they didn't. And what we're going to do is look at another one here. All right. Now, these ones are negatory. Okay. Here's some negative delta 17 on the horizontal, or on the vertical, delta 18 on the horizontal scale, and we got negatives. They didn't put the negatives in out here, but they put negatives down here on the vertical scale. And you can see, you know, this one is the oxygen in the sun, they think would be plotted up down here, and this one is oxygen in molecular clouds out in the universe that we see. And then here, this is a group of meteorites called Chandra. Actually, these are, Chandrul is a part of a meteorite that we think is a little nugget of the pre-solar nebula, undigested, unprocessed, and they're down here in the lower left quadrant as well, so they're negatives. CAIs, calcium enriched inclusions, these are also little sub-nuggets of given meteorites, and they're way down here in the depleted area. Now here's Mars, SNC, here's some asteroidal H2O over here, molecular cloud, water H2O, that's up here. And of course, SMOW of Earth is right at the very middle. 0, 0, make a note of that. On this kind of a graph, 0, 0 is SMOW. That's like putting 2005.20 divided by 2005.20 minus 1, and that's equal to 0. And the same thing for delta 17. So if you see something that's close to 0, 0, you know it's very close to standard mean ocean water of Earth. All right, so that's what, and if you go to that website, PSRD or any other one, you'll see these kind of graphs. And it's fun to think about it, especially if you think, well, why is, for instance, why is the oxygen gas of the sun so different from the oxygen in the water of the asteroids? Why is that? Well, the reason for that is some kind of physical and historical process that the oxygens in the asteroids of the water, the oxygen in the water of the asteroids, it went through a different process than the oxygens that we see in the surface of the sun. I mean, we see different elements in it's mostly hydrogen, but we see absorption and emission lines from oxygen and other elements like helium. That's a big one. So it's kind of fun to look at these things and think, well, why is it so different? You know, why is Mars slightly above the Earth-Moon line? You know, why are the Vesta fragments slightly below it? You know, and we're going to be getting to McKeegan. McKeegan is way out of there. All right, so hit your refresh key on your calculator. Okay. And let's do a calculation. Here it is. You're going to do delta 17 for Kalahari 008 as promised. And let me get the question started. And as you can see, Hannah, I'm telling you to go to the nearest 0.01 of per mil. All right. So get your ratio, go to percent, and then go to per mil, and then give me 2 decimal points of per mil. All right. So if you have like 0.045392, then type in 45.39. And then hit the send key. All right. So take a few minutes, and as always, consult with your neighbor, you know, studying with a friend, making a friend, hopefully not making an enemy. It's good to do if you can. Good. I see people pointing at the screen, talking to their neighbor. Good. Hannah, how you doing back there? Oh, really? Good. That sounds confident. Good. It's not like a bodacious calculation or anything, but it's not something cinchy like, you know, 7th grade distance equals speed times time. You know, that's something you learn. This one you don't learn in 7th grade at all. But if you ever go to like an astronomy colloquium over in the physics department, and you ask almost any of the planetary science guys, oh yeah, the delta 17 oxygen ratio, and their eyes will go, what? You know about that? So this is like, let's see, 73 answers. Give me 2 decimal points. I see a few of you have 3 decimal points here. Oh boy, I see a few of you are blooped up. Yeah, question. No, round normally up or down to the nearest point something something of per mil. So get it in, so do your calculation, then convert to percentage, then 1 more decimal point to per mil, and then give me the point something something. Round off carefully. Got it, Casey? Yeah, it's not too, once you know how to do it, it's not too bodacious. One minute. And you guys are doing pretty good, actually. Don't be blabbing like so loud. People blabbing out answers. I don't know. 30 seconds. Ten seconds, starting now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And good. All right. Let me show you the let me turn the lights back down. Yeah, the correct answer is 3.32. 58% of you got it correct. Now, I want to point something out to you. If, you know, by some chance, some outside chance, you do have a question like this on exam 3, and if by some crazy, wild chance it ends up on the clicker page, it might be a 3-point question because it's a fairly deluxe calculation and it's a little tricky, especially if you have a negative delta 18 or delta 17 ratio. If it's a 3-point question, then these guys up here at 3.32, they get 3 points. Now this guy, 33.17, rounded off incorrectly. So I might give that student 1 point instead of 3, partial credit. This guy, 0.33, rounded the other way incorrectly, So I might give that student 1 point partial credit. Now this guy here, 3.31, they're in the right area, but they rounded down instead of rounding up. And so I might give them 2 points out of 3. All right? And I don't know how you get 21.88, but, and you can go down and look at the different. So there's 33.1599. That's somebody that didn't round off. 3.316, another one that rounded off incorrectly. 3.317. You see where this, so when I'm looking at your guys' scores, sometimes I can't make out 0.32. Okay, that's a little bit too much round off. Sometimes I can't make out the 0.995. That's 1. Sometimes I can't make out the errors, but sometimes I can. 3.3. Right, see, these guys might get 1 point. But like 7.51, I don't know how to give a point to that, so they'd probably get a zip. But anyways, I just want to point that out to you. That's how we do that. Question? Yeah. Repeat? I can't hear you. The correct way? I think I have it spelled out on the next. Let me switch back over. There's your answer. I don't have it. I don't have it on the next slide. But what you would do, 381.16 divided by 379.9, and that's going to give you 1.00317, I guess. Is that about right? And then you subtract the 1, and then you, okay. So maybe I'll do an example in the homework in the instructions just to make sure you have some additional guidance. All right, now let's take a look at some more isotope data. And don't feel like you have to, jot all this down. Here's NWA 7304. We already talked about that baby. And that's an achondrite of Vesta. So that's a little hunk of Vesta. NWA 5721, NWA 2904. Those are all chunks of Vesta. Then there's, towards the middle, there's 3 Martians, ALH 840001, NWA 6162, and Yamato. And then Dofar, Galb, and Lynch, those are lunar meteorites. And let's see, this one right here, 4.6, that's ALH, no. 3.811, that's NWA 8157. It's got a negative delta 17 oxygen rating, okay? And that appears to be the only one. Now, McKeegan, the McKeegan particle that they found, that hotspot, look at the numbers for it down at the bottom of the table. Go ahead and make a note of this. Make a note of McKeegan, all right? Because I'm actually going to plot this data, and I think you can actually make a sketch of this plot, all right? And you're probably going to want to have some room to draw, because the McKeegan particle is way off the charts here. All right, so negative 117 for delta 18 and 1660 for delta 17 on the McKeegan particle. All right, so now here's the meteorites and stuff. The CM meteorites are the black squares. The chunks of Vesta are the blue triangles. SMOW, I've got my two blue dashed lines kind of over to the left and middle for the horizontal for SMOW. All right, so delta 18 oxygen horizontally, delta 17 oxygen vertically, and 0, 0. So right down here is SMOW. So that's Cocoa Beach. Okay, so if you go to swimming in Cocoa Beach, this is where your toes dipped into the water are. Okay, but over here, these guys, different process. They're not oceans. They're hunks of planets and other asteroids and stuff. All right, now here's a close-up. It's a return view to this thing. We already looked at it. Okay, and so you can see Vesta. The Vestas are down here, and the Mars are up here. Earth, Moon are right through the middle. And here's my plot again. I don't have any Earth rocks. You know, what I should have done is put some, I don't know, you know what I should do is a chunk of Florida limestone. Put a couple of those, and the PD ilmenite belemnite limestone up in South Carolina, and then put those on this plot. I'll try to do that for next semester. Anyways, so the lunar one's up here. So lunar is a little bit below Mars. I don't have any terrestrial, but I do have a couple lunars up here. Okay, here's Vesta down here. Here's SMOW, the blue dot at the origin. Okay. And now McKeegan is way to the left, and it's way, way up. All right. Here's the McKeegan numbers again in yellow. Negative 117 in oxygen 18. So it's depleted. It's not grossly depleted of oxygen 18, but it is significant, especially relative to these other meteorites and stuff, because it's a different process. What it went through, that little grain of a red giant star, is different from what asteroids and meteorites have gone through. And it's way hot in oxygen 17. All right, so here's my graph again. All right, and here's my table. Oops, I'm going backwards. Let's go through this again. Okay. Here's oxygen. Okay, now we're going to graph up McKeegan. But before we do that, I want to answer this question. What the heck is McKeegan? Well, this is Mr. McKeegan, professor of planetary sciences out at UCLA. He's the primary author of that article. This is the big shot. Okay, and very famous guy. And here's his isotope separator. Okay, so this is his big, in other words, it fills a room. You can see a desk here for a human right here. So this thing basically fills most of a room. You could probably put a couple, 3 of them inside this lecture hall, but it's fairly big. And he vaporizes stuff and sends it through these tubes and stuff. And here's one of his analyses. This one is carbon. And this one's a little different than the one we were looking at. This is carbon and nitrogen kind of side by side. So this is not oxygen 17, oxygen 18. It's carbon and nitrogen isotopes. And then you could do that as well. All right. So now here are the famous bullet holes. And here's my hot spot right up here. Bing, this little guy, red as can be. There it is. The residue. Here's the pre-solar grain. And there it is. There's the hot spot. All right, now we're going to graph that up. It's actually 1660. And so here's all the, nice, lovely meteorites, lunar, Vesta, Martian, very nice. But here's McKeegan way out here. Whoa, way out here, baby. All right, and here's Earth. This is the terrestrial stuff down here, and here's McKeegan way up here. So when they got McKeegan is way out. And last time I was emphasizing, it is from a whole other star. It's like this whole other, whole other part of the galaxy. And, that star blew up at least 5 billion years ago as a supernova probably, and blew nuggets everywhere, and they pulverized smithereens, and they swirled around out in the nebulas and stuff, and got spinning, and then that little nugget and a bunch of other ones eventually spiraled down and conglomerated together to form SUN, Jupiter, Saturn, and every other planet, every other comet, every other asteroid. But this one never got processed. It's like somebody... Here's what it's like. It's like an asteroid from the space station walking around in his spacesuit. He doesn't need it. And most astronauts are going to take off their spacesuit, when they get back down to terra firma. All right? And this is a little piece of a star, 5 billion years plus in age, and nothing has happened to it to process it into like the water that we find in the asteroids or anything else. It's way far away from SMOW. So when we say that this thing is conspicuous, this graph shows you what that means. It's way outside the boundaries of all these other things. Most of the stuff that where's my cursor? Come on, baby, here we go. Most of the stuff that we pick up from asteroids, meteorites and stuff, it's over here, inside this little square over here. But McKeegan, bang, that thing is way out here. Oh man, I tell you, all right. So here again is the money quote. This isotopic composition, way out here, up and to the left, is typical for pre-solar oxide and silicate grains belonging to Group 1, a group of stars that's thought to originate in red giant or asymptotic giant branch stars. And there's the citation for Kevin McKeegan et al. Now, as Forrest Gump says, that's all I have to say about that. But I have a lot more to say about the SUN. That's our next topic. But before we do, let me pause for questions about McKeegan and isotope ratios. Yes?
On the graph, what does
CM
CM stand for?
stands for, the M, I believe, stands for a certain, CM is a certain class of meteorites. We find all kinds, like some meteorites are just metal. They're iron and nickel, right? Some really big ones too. And some are like, rock. They're pieces of Mars, pieces of the moon. Those are more rocky. And so they classify them. And CM is a class of meteorite. Okay, and I think it's some kind of M that has a lot of chondrules in it. It's a chondrite. So a chondrule, I forget what the Greek word for the Greek root word behind chondrule. I can't remember what it is, but it's like a little nugget of the pre-solar nebula that never got reprocessed. Okay, kind of like McKeegan is a little nugget of a red giant star that never got reprocessed. All right, so it stands out from everything. All right. Another question. Yes, Vince.
When you say that
depleted. It means it's not enriched. It has less oxygen 17 than SMOW.
Okay, so but is there like a zero out point where there's like no?
Yeah, if it has exactly the same abundance, you know, for delta set. So if you find a rock that's got exactly 379.9 parts per million of oxygen 17, then your numerator of the fraction is 1. Then you subtract 1, and you get 0. So its delta 17 ratio is 0. In other words, it's exactly the same as SMOW, right? I don't know if there's any rocks that are exactly there, but there's probably rocks that are close.
Yeah, I mean, like, is there a point where there's no oxygen in the meteorite?
Oh, well, yeah, you know, some meteorites are metal, you know, like iron, nickel. And, you know, the core of the Earth is iron and nickel, we think. You know, it's, you know, molten liquid metal. You know, it's either that or, you know, so like a lot of the meteorites are metal and stuff. And it's either that or it's, you know, liquid metal terminator, one big liquid metal terminator down there. I don't know. But yeah, I mean, so the metals are probably going to be really, really depleted, you know, like negative 7,000 or negative 7 million or something. In other words, not much oxygen. And, you know, and a meteorite's going to pick up a little bit as it goes through the atmosphere. It's going to oxidize a little bit. So probably there, you know, but if you take a chunk from the middle of the metallic meteorite, it's not going to have much oxygen at all. All right. All right, let's talk about energy. And we're going to be talking about the SUN. The sun is a natural fusion reactor. So what we're going to actually do is talk about energy. The core of the sun, these are comments from chapter 15 now. That is where the nuclear fusion reactions occur. Now, the entire sun is not undergoing fusion reaction, hydrogen fusing into helium nuclei. But in the core, yes, there's abundant fusion reactions. You know, outside the core of the sun, it's just really, really hot hydrogen mixed with helium. It's boiling and toiling and stuff. And so the sun is hot because of the fusion reactions that have occurred and continue to occur. Now, this is what a pre-solar nebula looks like. Now, this is for the star called HL Tauri. All right, and so and actually, this one is got planets. You can see those dark lanes, the dark orbits. Those are big planets sweeping the solar nebula. So the solar or the pre-solar nebula, it swirls and burls and stuff and eventually starts spinning, and it also starts conglomerating into planets, into comets, and you know, and comets smack into other comets and become bigger comets, and planets smack into other planets and become bigger planets. But in the middle, there's going to be something big enough, usually, to form a star like our sun. And this is what our sun looked like, you know, maybe 4-point-something billion years ago. All right, we think the sun is about 4.6 billion years old. Okay. Now, the sun structure is pretty important. And this is a lovely diagram. It shows the core, the photosphere, the corona. It's even got some sunspots. The outermost part of the sun is the corona. It extends millions of miles into space. Okay, and it's the part that you can see. It forms like a crown, a corona, when you observe a total eclipse, like we had back in the autumn. in between the corona and the core, there's a lot of physics going on there. It's not, so there's not any nuclear reactions, but there's a lot of electromagnetic interactions. And for instance, sunspots are related to intense magnetic fields that form in the surface of the SUN. You know, if you think about it, you know, an electromagnet is what you get when you have a current that goes in a circle of some kind. If you got a little bit of electrical current, you know, going around in a circle or a coil, it'll form an electromagnet. And, you know, many of you have done a science experiment in grade school, you know, for science fair. You know, you take a battery and you take a wire and a nail and you wind the wire around the nail and then connect the wire to the battery, and the nail is now an electromagnet. You could pick up paper clips and stuff like that, you know. And I've done that, and if you do it with too many batteries, you can, you know, burn yourself, so you got to be careful, but it'll form a nice little electromagnet. And the same thing's happening in the surface of the sun. You get these currents of ionized atoms of hydrogen and helium, and anything else that's around there, a little bit of oxygen, a little bit of neon, they get ionized, they're charged, they're in motion, so that's like an electric current, all right? And what makes a looping electric current is convection. So you have to keep into account the thermal fluid properties of the outer layers of the sun as well. There's huge convection cells. Just, you know, and a convection cell here in our state is a thunderstorm. You know, those storms that we had blazing through the other day, Tuesday night, you know, that were dropping all that rain and causing all that thunder and lightning that was so scary. Did anybody see a tornado? Raise your hand if you saw a tornado. I don't know if anybody. Did you see it? No? Yes? Where were you? Like by Ocoee or something?
Yeah, I don't remember exactly. I was like at a doctor's office.
So were you like, did you? Did you call your mom? All right, that's good. Hey, raise your hand if you saw big hail on. I didn't see any. I drove, you know, when I was driving home, I was driving right into this zone where they said there was 2-inch hail falling. Anybody see like ping pong ball size hail or bigger? A couple of you. I thought I was driving. I mean, I didn't deliberately do it, but I had to get home. And my wife was all upset. And it must have just went right around me or something. Those jerks. So I didn't get to see any cool tornadoes or hailstones or anything like that. But all right, so let's do a little primer in energy concepts. And so this is kind of pre-reading in chapter 16. Energy and luminosity in the metric system. Energy is measured in joules. On your power bill from Progress Energy or from Duke Energy, it's kilowatt hours, but so something can have kinetic energy. Something moving, a 2 kilogram object moving at 1 meter per second. Here's the formula, 1/2 mv squared. And a joule is the kinetic energy of that object. You know, 1/2 times 2 times 1 squared is equal to 1. And so a 2 kilogram object moving at 1 meter per second. So that's the metric system. And there's other there's other units of energy. In the English system, I have to think. Foot-pound is actually, in the English system, a unit of energy. But we don't do any astrophysics in foot-pounds. Luminosity is in watts. Okay, so like the bulb that you buy, the old-time incandescent bulbs, you get one that's 60 watts. Or if you have a little, like a refrigerator light, it might be 2 watts, because it doesn't have to light up a whole big area. Or a big, bright lamp in your living room might be 100 watts. And nowadays we have LEDs and stuff, but the LED light bulbs always say replaces, 60-watt bulb, or replaces 100-watt bulb, meaning it puts out the same amount of light without as much energy. Now, a watt is a joule per second. All right, so for an incandescent light bulb, you're talking 60 watts. The sun, the luminosity of the sun is a lot bigger than that. It's approximately 3.8 times 10 to the 26 watts. All right, so jot down the sun's wattage rating. And let me invite you to recall that the solar constant for our planet is about 1,367 watts per square meter above the atmosphere of the Earth. So if you're on the day side of the Earth, and you take a 1 square meter window, there's about 1,367 watts of solar energy hitting that window. So if you could convert it 100% to electricity, you could run like a hair dryer or something like that. All right. Now the sun has this huge wattage rating, and go ahead and make a note to yourself: a watt times a second is a joule. 1 watt second is a joule, because 1 watt is a joule per second. So 1 watt times a second is a joule. 1 watt times a minute is 60 joules. A watt minute. A watt hour is 3,600 joules of energy. A kilowatt hour is 3,600,000 joules of energy. And for Progress Energy, it costs you about 9 cents for a kilowatt hour of energy. So Duke Energy sells you kilowatt hours, and when you look at your, for those of you that pay your heat bills and your electricity bills, it'll be in kilowatt hours, and there's various rates per kilowatt hour, but that's a unit of energy. All right, now some other examples of energy. Okay, let's say you have a Bumblebee Camaro and a quarter mile, 115 miles an hour, 12 seconds. Yeah, kinetic energy is 2.2 million joules. All right, so you would write that down, 2.2 megajoules. A tank round from an M1A1 Abrams, pictured here, is about 12 megajoules. And the Navy's new railgun, supposedly hypervelocity projectile, 32 megajoules. All right. And a lot of times the round from a tank is not explosive round, it's kinetic energy. A big piece of metal, high density metal. Same thing with the railgun. So the power rating, and let's just jot down our rating. 2.2 megajoules to 12 seconds. So the average wattage rating for the Camaro is 176 kilowatts. Hair dryers are about 1.75 kilowatts. So about 100 times more to power a Camaro. All right, it's 10:14. Let's dismiss. I'll set up homework available probably tomorrow night, due on Tuesday. You're dismissed. And we'll keep going with this.